Well, chapter 4 is dedicated to scattering and to alternative techniques to compute the scattered fields that are not based on numerical methods. That is, they are not based on solving a linear system of equations or an iterative procedure to solve a differential or integral equation. That is another kind of either exact analytical methods or approximate methods. The first part will be just dedicated to the definition of radar cross-section, which is the magnitude that we use to measure the strength of scattered fields. Then there will be a second part dedicated to canonical problems, that is problems that have an analytical solutions, and I will show you how to solve these problems analytically. And the third part is dedicated to high frequency approximations, that are approximate methods that can be applied when the object is very large compared to the wavelength and it is not possible to analyze it using numerical methods due to the very large number of resulting unknowns. And then we have approximations that are valid in these cases, in the cases where the object is very large compared to the wavelength. So the first part, these are the three parts that I mentioned: the radar cross-section part, the solution of canonical problems, analytical solution, and then high-frequency approximation. So the radar cross-section. Well, radar cross-section is the magnitude that we define to measure or to represent the strength of scatter fields. And it is very important because now, we have a radar that produces an incident field, and then the magnitude of the scatter field is very important. Then we have another receiving radar that very often is the same as the transmitting radar. But the magnitude of the scatter field is very important because when we have, for example, a civil target like an aircraft for the transportation of people, we want it to have a very high scatter field so that it is easy to be detected by radar. But on the other hand, military aircraft want the opposite. They want to have a low scatter field so that they are difficult to be detected by radar. So at the end, the specification of the radar cross-section, that is the magnitude measuring the strength of scattering, is important when we design an aircraft or a ship or whatever, that an object that can be detected by radar. For some applications we want a high radar cross-section, and for other applications they want a low radar cross-section. So at the end it is a very important magnitude that it is specified together with the speed of the aircraft, the weight, the payload that it can transport, etc. The RCS, or radar cross-section, RCS stands for radar cross section S, and it is a very well known magnitude that you must be aware of, and very important one. So the definition of radar cross-section is the following. It is the area, it is represented by sigma letter. It is the area intercepting an amount of incident power. So if the incident power is like this, we have here some incident power, the aircraft has an equivalent area. Let's say, for example, imagine that this is, better in black color to make it more visible. We have an equivalent area, so that area intercepting the amount of incident power, so the amount of incident power will be the intercepting area which is sigma, the radial cross-section, times the incident field, power density, and this is the intercepted power, okay? So the area intercepting that amount of incident power, which when scattered isotropically, so the target scatters isotropically this intercepted power, okay, and produces at the receiving radar antenna a power density equal to that scattered by the actual target. So the power density scattered by the actual target, rho s, is equal to the power density isotropically scattered by the intercepting area or radar cross-section. So, since the intercepted power is the product of the incident power density rho I times the intercepting area sigma, this intercepted power over 4 pi r square over the surface, this is the surface of the radiation sphere, this is the radiation sphere, okay, of radius r. So 4 pi r square is the surface of this sphere. Then the intercepted power that is radiated over the surface of the sphere is equal to the scattered power density of the actual target. So here, of course, this is at large distance. This is, we set this observation distance r to infinity because it is at very large distance, so it is using far field equation. Remember far field approximation in the radiation equations. So it is at very large distance, okay? So here we isolate the radar cross-section and we get the radar cross-section is equal to the scatter power density here over the incident power density, okay, times 4 pi r squared, that comes here, okay? And of course this is in the limit of very large observation distance. Now we remind that the power density of a plane wave, and I say a plane wave because at very large observation distance a spherical wave is locally equal to a plane wave, as you know from chapter 1. The scatter power, the scatter power, and also the incident power. So I removed the superscript because this is valid both for scatter and incident power, is equal to the square of the electric field over the wave impedance. So the wave impedance cancels out between the scatter power density and the incident power density. The two wave impedances in the numerator and denominator cancel out, and we get this equation. This is the important equation, okay? That the radar cross-section is the limit for very large observation distance of 4 pi r squared times the square of the scatter field magnitude over the square of the incident field magnitude. Here we have missing the arrows of the vectors. And now we will see two examples, two important examples, the sphere and the flat plate. For a sphere, clearly the projected surface intercepting incident, this is the incident power density, so the projected surface of the sphere, if the radius of the sphere is a, the projected surface is pi a squared, so that the intercepted power is the incident power density times the projected surface pi a squared. The sphere really scatters power isotropically for a radius of the sphere that is very large compared to the wavelength. We will see this later in the part of this chapter dedicated to canonical solutions. We will obtain the analytical solution of the scatter fields for the sphere. and we will see that it is almost isotropical for very large sphere radius compared to the wavelength. So here we assume that power is scattered isotropically, but this is not the definition of the radar cross-section, because we have isotropical scattering in the definition of radar cross-section. No, this is not the definition. This is what truly happens for a spherical scatterer. Okay, this is what truly, it is really almost isotropical scattering. Okay, so the scatter power density, the real one, the true one, is the intercepted power, which is equal to the scatter total power if there are no losses, times, over 4 pi r square, where r is the radius of the observation sphere, and 4 pi r square is the area of the observation sphere. Okay, so this is the scatter power density. So we substitute this scatter power density in the formula of the radar cross-section. We substitute we have the incident power density here. It cancels out, and what we get is that the radar cross-section is equal to pi a square. That is, the RCS, which is the equivalent intercepting area, is equal to the projected surface of the sphere. And this is only because the sphere scattering is isotropical or almost isotropical, which is the same as the isotropical scattering defined in the definition of RCS. So in this case, we get that the RCS is equal to the true projected area of the sphere, which is pi a square. Later, we will obtain this, and we will obtain the analytical solution, and we will see that the analytical solution is almost pi a square when the radius of the sphere is much larger than the wavelength in high frequency. Okay? Now a different case, also an important case. This is the flat plate. For a flat plate, the plate is perpendicular to the incident direction, so the normal to the surface is parallel to the incidence direction. Okay, this is perpendicular plate. So the projected surface is equal to the area of the plate A. Okay, and the intercepted power is the incident power density times the intercepting area, which is A. And now the scattering of the flat plate is not isotropical like the scattering of the sphere. The scattering of the flat plate is directive. It has a radiation pattern like this, and in fact it is the same radiation pattern as that of an aperture antenna with uniform illumination, with uniform field in the aperture of the antenna. You know that if the field, an aperture with uniform field has aperture efficiency equal to 1, or illumination efficiency equal to 1, so that the effective area of the aperture is equal to the area of the physical area of the aperture. In this case, the aperture is the plate, so that the directivity that the directivity is 4 pi effective area over lambda square. In this case, the directivity is 4 pi surface, the physical surface of the plate, which is A, over lambda square. And then we use the definition of directivity. Remember that the definition of directivity is the radiated power density. In this case, the radiated power density is the scatter power density rho s over the average radiated power density, and the average is the total radiated power over the radius, over the surface of the radiating sphere, again 4 pi r squared, where r is the radius of the observation sphere. This, again the same thing, and we know that the total scattering power is equal to the intercepted power if there are no losses, and the intercepted power is equal to the incident power density times the intercepting area A. So we substitute this, and we isolate here the scatter power density as a function of the directivity, and then we substitute the formula to compute the directivity here, and we substitute the scatter power density in the definition of the radar cross-section, and what we get at the end is that the radar cross-section of the flat plate with perpendicular incidence is equal to the directivity of the plate times the area of the plate. And substituting the formula for the directivity of the plate, we get that the radar cross-section of the plate is equal to 4 pi, the square of the area of the plate over the square lambda. And this is approximately the same that we get using high frequency approximations in the latest part of this chapter. We will obtain the same formula using physical optics approximation. But in general, for directive targets, the RCS, the radar cross-section, is not the area of the plate as for isotropical scatterers like the sphere. We got that the RCS was the area of the plate. So in the case of directive targets, we have to multiply by the directivity of the target. That in the case of the sphere, the directivity was 1 with isotropical scattering. But if the directivity is not 1, we have to multiply by the directivity. So in general, the radar cross-section or equivalent intercepting area is equal to the true physical intercepting area times the directivity of the target towards the receiving radar antenna. The radar cross-section is very often represented in dB scale, logarithmic scale, because there is a huge range of possible values of radar cross-section. For example, very large targets that are much larger than the wavelength have very large RCS values of tens of thousands, or even in extreme cases hundreds of thousands of square meters. But on the other hand, small scatterers have RCS less than 1 square meter. So the range is so large that we very often express it in dB, in logarithmic scale. Of course, we have to use 10 logarithm because it is a power magnitude, and since it is a power magnitude, you know that you have to use a 10 logarithm. And the name of the unit is dB square meter, dBsm. We often say dBsm, which means dB square meter, because it is a relative, the RCS is an absolute magnitude, the units are square meter, so in dBs we have to represent a relative magnitude, so we represent the RCS relative to 1 square meter. So it is called dB square meter, and it is just the 10 log 10 of the RCS in square meters, okay? Now we have also to distinguish between bistatic and monostatic. In general, we have a transmitting radar and a receiving radar, and they don't have to be at the same location. In this case, the very general case in which they are at different locations is called the bistatic case. So it is bistatic, okay? And if the receiving radar is the same as the transmitting radar, the receiving and the transmitting radars are the same antenna, then it's called monostatic radar. And this is the most common case. However, the bistatic case is also possible. And if we want to account the effect of polarization, for example, imagine that the transmitting antenna produces an incident field with vertical polarization. This vertical polarization will be the copolar polarization here. The scatterer depolarizes the field, and the scattered field has both polarizations. The copolar one, which is the same polarization as that of the transmitting antenna, but also the cross-polar polarization, which is the polarization orthogonal to that of the transmitting antenna. And this scatter field has the two polarizations because the total field which is, remember that the total field is the sum of the incident field plus the scatter field according to equivalence remember equivalence theorem formulation, etc., etc. And this total field has to agree with the boundary condition. For example, imagine that it is a perfectly conducting target, so it has to agree with a boundary condition of the tangent component of the electric field equal to 0, and if it is an arbitrary surface with curvature, it is necessary that the scatter field has cross-polar components to agree with the boundary condition. So automatically the polarization of the incident field is automatic due to the curvature of the surface of the scatterer. In this case, we can represent the RCS as a scattering matrix. That is, for example, if we have an incident vertical polarization, this is incident vertical incident polarization, we have two possibilities: the scatter field in copolar polarization, or scatter power in copolar polarization, and scatter power in cross-polar polarization. So in this case, since copolar was vertical polarization, we have two magnitudes that are vertical, that is incident vertical and scatter vertical, and then horizontal vertical, which is incident vertical and scatter horizontal. But we have to make the computation also for horizontal incident polarization. In this case, the copolar polarization will be horizontal, and we measure or compute the scattering both at the horizontal polarization, which in this case is the copolar one, and the vertical polarization, that in this case is the cross-polar one. So in this case we have two other terms of the scattering matrix, because this aggregation of the four possible magnitudes or four possible combinations is called the scattering matrix, and it has here the horizontal incidence and observation in horizontal or vertical polarizations. So the scattering matrix has four terms. The rows correspond to vertical or horizontal scatter field or scatter power, and the columns correspond to vertical or horizontal incident power. Of course, it is obvious that we can obtain the scatter power in vertical and horizontal polarizations if we multiply the scattering matrix times the incident power density in horizontal and vertical polarizations. Okay, this is incident. This is the use of this scattering matrix. We can write a radar equation that relates the total received power at the receiving radar compared with the total transmitted power at the transmitting radar, that is analogous to the transmission equation in a radio link. In this case, it's just a radio link, but that between the transmitting radar antenna and the receiving radar antenna, but with the effect of the scattering at the radar target. So We assume that we have a polarization match case. In this case, we don't have to account for the scattering matrix. And in this case, we know that at the receiving antenna, the total received power is equal to the effective area of the receiving antenna times the received power density. The effective area of the receiving antenna, you know that it is the directivity of that antenna over lambda square times lambda square over 4 pi, but if we account for losses, we replace the directivity by the gain, so it is the gain of the receiving antenna times lambda square over 4 pi. This is the effective area, and to compute the received power, we have to multiply by the received power density. Okay. Then the received power density is computed from the definition of RCS, and remember that if we remember that in the definition of the RCS we said that the RCS is such area that as intercepting the incident power density, and this is the intercepted power. This radiates this intercepted power, and the radiated power or radiated power density or scatter power density will be the total radiated or re-radiated power over the surface of the radiating sphere, that is 4 pi r squared. Now it is R2 because R2 is the distance from the target to the receiving antenna, so this is R2 to the receiving antenna here. And now we also have an equation for the incident power density that depends on the definition of the directivity or gain, if we account for losses, of the transmitting antenna. From the definition of gain or directivity of the transmitting antenna, we know that the power radiated by power density radiated by the transmitting antenna, which is equal to the power density incident on the target, is the total radiated power times the directivity or gain in the case of losses of the transmitting antenna over 4 pi r1, where r1 is the distance from the transmitting antenna to the target, and 4 pi r1 square is the surface of the transmitting spherical wavefront. Okay, so we replace the incident power density. The incident power density is replaced here, and we rapidly get that the total received power over the total transmitted power is equal to the radar cross-section times the product of the gain or directivity in case of no losses of the transmitting antenna times the gain or directivity of the receiving antenna over 4 pi times the square of lambda over 4 pi r1 r2, where r1 is the distance from the transmitting radar to the target and r2 is the distance from the target to the receiving radar. So this is what we got in the previous slide, and this is valid for the general case of bistatic radar. However, in the case of monostatic radar, remember that the receiving antenna is the same as the transmitting antenna, so that R1 is equal to R2 equal to R, and in this case the radar equation becomes slightly simpler, becomes essentially proportional to the inverse of the fourth power of the distance from the radar to the target. And this is very important. This proportionality with r to minus 4 is very important, because this means that when we double the distance between the radar and the target, we get 16 times less power, which is a lot, and this makes difficult the detection of radar targets that are very far away from the radar. However, and the surveillance radar at airports or military surveillance radars are able to detect targets at distances up to 500 kilometers, which is a lot. Imagine 500 kilometers to power minus 4. The received power is very, very low. So the radar has to be very sensible. But the radar also has to transmit a lot of power, usually hundreds of megawatts, I repeat, and the gain of the antenna is very large, like 40 dBs or something like that. So if we combine a very large antenna with a very large transmitted power, we can still detect radar targets at hundreds of kilometers of distance. We can isolate here the maximum detection range as a function of the minimum received power. This is the sensibility of the receiver, the minimum power that the receiving antenna must receive to detect the target, and it can be very low because the receiver is very sensible, but also because signal processing makes it possible to receive signal power that is even less than the thermal noise due to intelligent signal processing or just old signal processing, but there are signal processing techniques that are able to detect very low incident powers. Okay, so we can see that this maximum detection range varies only at the fourth root of the RCS. Well, do you remember that in chapter 3 about numerical methods we defined two-dimensional problems that were problems in which everything is constant in set coordinate, nothing varies in set coordinate, so the only variation is in x and y coordinate. Remember that you did, for example, in practical project 2, you did the analysis of two-dimensional objects, that is objects that only depend on x and y coordinates. So we can compute the two-dimensional RCS in a similar way. I just remind here in this slide, I remind you the definition of two-dimensional problems. These are problems in which the object is constant with respect to set coordinate, that is, the surface of the object doesn't depend on set coordinate. It is exactly the same in all planes that are perpendicular to set axis. So if the object surface does not depend on set coordinate and the incident field also is independent on set coordinate, then the scatter field will be independent on set coordinate, and all the magnitudes like current, charge, etc. will be independent on set coordinate. All magnitudes will depend only on x and y. For this reason, we call this problem a two-dimensional problem, because we only use x and y coordinates to represent all magnitudes. Of course, the space is three-dimensional, so it is a three-dimensional problem where the object is infinite in set coordinate and all the magnitudes and the object surface are constant in set coordinate. Okay, but we call it a two-dimensional problem, and you know how to solve it using numerical methods. Of course, we can use Cartesian xy coordinates, but we can also use polar rho and phi coordinates instead. Now, we can define the radar cross-section for two-dimensional problems. First, I remind you the definition of RCS in 3D, in three-dimensional problems, as the limit for a squared observation distance r, or distance to, this is of 4 pi r squared times the scatter power density over the incident power density. And remember that this 4 pi r squared comes from the fact that the scattering sphere, or the spherical wavefront of the scatter field, the scattering surface, has an area 4 pi r squared. Okay? So in two-dimensional problems, what we have? In two-dimensional problems, we have a scattering cylindrical object independent on c coordinate, and the scattering surface, that is the surface of the scatter wavefront, is cylindrical. So the surface here is equal to the radius of the scattering cylindrical wavefront, which is rho, times 2 pi, which is the circumference of the spherical, the cylindrical wavefront, times the length, the height of the wavefront. But here, since the height is infinite, we represent everything per unit, we compute everything per unit length. So we multiply by 1. So the surface is 2 pi rho. So we replace here the 4 pi r squared of three-dimensional problems is replaced by 2 pi rho in two-dimensional problems, because the surface of the scattered wavefront is the circumference of the cylinder, 2 pi rho, remember rho, the distance to the z-axis, times 1, which is the height when we compute magnitudes per unit length. Okay, and then replacing the power density by the square of the field magnitude over the wave impedance, we get that the two-dimensional RCS is the limit for very large rho, observation distance rho, 2 pi rho times the square of the scatter field magnitude over the square of the incident field magnitude. But in practice, you know that the scattering of objects in practice cannot be infinite. In practice, what we have is a finite cylinder. This is a finite cylinder having a length L, finite length L, but when L is much larger than lambda, remember that the dimensions in electromagnetism, in radiation and scattering, the dimensions are relevant only compared to the wavelength. So if the height of the cylinder is very large compared to the wavelength, we can assume that the height of the cylinder is infinite. And we can obtain a relation between the scatter field by the infinite two-dimensional cylinder with the scatter field of the finite three-dimensional cylinder of height L. And this relation is the following. The scatter field of the finite three-dimensional cylinder is approximately equal to the scatter field of the two-dimensional infinite cylinder times the length of the three-dimensional cylinder L plus additional phase of 45 degrees over the square root of the wavelength and the scattering distance rho. Okay? And this is valid for normal incidence. This equation is valid for normal incidence. So we can see here that the incidence direction is at 90 degrees from the incidence direction is at 90 degrees from the Z axis, that is the axis of the cylinder. Then, replacing these three-dimensional and two-dimensional scattered fields in the formulas of the three-dimensional and two-dimensional RCS, we get the final and useful formula that the three-dimensional RCS of the finite three-dimensional cylinder of length L is equal to the two-dimensional RCS of the infinite cylinder, and remember that this is an RCS per unit length, times twice the square of the length over the wavelength. And this is an important and very useful formula. Just to finish, to remind you that the two-dimensional RCS, it is called a scattering width because it is an area per unit length in Z dimension, so in fact the units are meters, and it is also called scattering cross width, not cross section, but cross width. So it is as called scattering width, or rather scattering width, like that, etc. And it is often represented in dBs, so it will be dBs over meter, similar to the dBs over a square meter that we have in the case of three-dimensional scatterers.